Hello once again. Today our area of study is introduction to algorithms, and we'll be talking about the core concepts. Look at look at the analysis, and we also touch on control structures and problem solving. Let's continue. So, what is algorithm, or what are algorithms? Algorithm is a step-by-step, gradual, unambiguous procedure for solving a problem. What this means is that algorithm is the gradual or the slow, that is not too quick, not too slow, but it is the procedural way of trying to arrive at a solution. And it is all about accomplishing a task in a finite number of time. That is, as we are trying to accomplish a task, we are looking at the time that we are to exhaust or the time you are using to solve the problem. So it is definite. It means that it's finite. The time for the solution is known. So that is the brief understanding of an algorithm. It's ambiguous. It means that it is clear, it is understandable, it is devoid of and anything that will render any false idea about that thing that you are doing. So algorithms are good. Yeah, that it helps us. It gives us the breakthrough to quickly solve a problem within a short possible time, knowing what to do and how to do it. So the formal definition of algorithm is the abstraction of a computer program. So in the field of computer science, you look at abstraction. Abstraction is the concept of looking at instructions in a way that helps us to solve our problems. In the computer world, we know that computer use programs, and programs is a set of instructions that helps the computer to run smoothly and normally. So that is what we are trying to mean. And the origin of the term that is algorithm is derived from the Latin name that is from a Persian mathematician who was named Muhammad ibn Musa al Khwarizmi. That is Muhammad ibn Musa al Khwarizmi. That's the name. That was the origin. This is just the origin of the algorithm. That's how we have come over the years. That how we've come out with that concept, with the origin. That is where it comes from. And if you look at it stands on its own. It is not associated with any programming language. So the last, that is the under the algorithm, we can look at another section that is after we've talked about the formal definition and the origin of the term, which was from a Persian mathematician who was named Muhammad ibn Musa. And so algorithms are independent. So what it means is that they are not related to any specific language. If you pick the languages like Python, C++, Java, and even the machine code itself, it is unique for like if you pick the if you pick algorithms, step-by-step process of solving a problem or the ambiguous procedure for solving a problem. It is if you pick like a language like Python, realize that the step by step might be a little different from that of um, the other languages. So what it means is that it is not linked to any programming language. It is in its own uniqueness. Algorithms are on its own legs or its own umbrella. It is very unique. It doesn't follow any other programming language. So if you look at all the languages, we talk about how to solve a problem or you have an idea you want to implement using the code itself, like the language, like Python. You consider its algorithm, it is the same. That is, you look at the algorithm terms like search, sort, and all those things in its own programming language. You can look at it from that perspective of Python. It's simple. So Having a better understanding of an algorithm helps you to delve into so many programming language without the difficulty of you misinterpreting the language or being misinformed. Because if you have a very good or firm understanding of an algorithm or algorithms in general, how to solve a problem, how to come up with steps to make your solution very suitable, that is to stand the test of time. Realize that having that kind of knowledge helps in a long way to bring the gap or to make you versatile in all the languages that we have. That is that is it. Let's continue. So we also let's look at characteristics of a valid algorithm. Algorithms, as we said, they are step-by-step process. And in each step-by-step process, we have some qualities that we need it to have. First of all, an algorithm must have an input. An input means that it must have a well-defined quantities passed into it. That is, it must have an initial, that is, maybe initial acceptance or initial input of that nature. You must put things, you must put some, you must bring ideas. You must let us know what you are thinking. That is the input that we need. What you want, what you are bringing on board. What is your concrete steps you want to take? That is the input. And every step or every procedure you are implementing or you are going by have an outcome. What is the output? So it must yield at least one clear result. So that is the result. Every action has a consequence. There's a movie that is Spider-Man. He said, uh, with, with great power comes great responsibility. It's the same thing. Every input that we put inside a machine or any algorithm, when a clear output. In the statistics, that is, it must be definite. But that is definitely means that it must have a limit. So, and having a limit means that it doesn't, it is clear. So you're not missing words or your deadlines or anything. So each operational step must be crystal clear. And also the fourth step that we are looking at is the finance. Yes. And the finance means that it must the execution that we are implementing must terminate after countable number of complete or discrete steps or sequential steps. It cannot run forever. So um, that is the final case of how you want an algorithm to be. So if you have an algorithm, you must have these qualities that we are looking at. So the last one is effectiveness. That's the feasibility. Feasibility here means the possibility of something happening. So every algorithm or every solution that we want to go by must have the possibility of solving a problem. You ask yourself, is it capable of solving the problem I'm trying to solve? If that's not the case, it means that it's not effective. And if something is not effective, it's not potent. It means that it doesn't have the power to do anything. So get me. So what so under the effectiveness and feasibility, look at every step must be basic enough to be performed basically with raw mechanical operations. That is effectiveness. It must be effective. That's the basic. It must be basic enough to perform practically with raw mechanical operations. So that is the. Let's move on. We also look at the methods of algorithmic representation. How do we represent algorithms? The next one, the first point or the first representation is natural language. That is our language, our how we speak, the descriptions that we make, and and it's easy for humans to understand that we are prone to linguistic ambiguity and semantic confusion. So if you look at the human the human perspective and the algorithms in general, humans we use plain language, that is, and normally the languages we use to express ourselves in the like English or French and the other languages, which is very that's what we use. So that is one way of letting all of us know your solution. That is speaking it out in plain descriptive form, that is dialects that we can understand. Also, we can talk about the pseudocode. Pseudocode, what does pseudocode mean? Pseudocode is the informal, high-level structural narrative blending programming language, and it lacks strict compiler intuition. So what we do with that? A pseudocode is just an informal form of writing code. Yes, we write code. That doesn't mean anything. It's false. We don't intend to run it anywhere. We are just trying to you are just letting us know your logic. That is how we intend to solve something. We also have flowchart. Flowchart is the grammatical representation of data and or of a problem or of a solution. How you intend to solve a problem. That's using diagram to present your ideas and stuff. The last point that that's the method one, the last method we can use to uh, visualize our algorithm is the programming code itself. That is the use of languages like Python, C++, using the actual code that we can compile and run on a powerful physical machine. That is it. So we also looked under the methods of representing algorithmic presentation. We looked at the section which is flowchart. And flowchart is a very key section that we have to look at it. So if you look at the standard flowchart element, flowchart is it is a diagrammatical expression of a solution. So we have elements within flowchart, or we have symbols used to represent various actions. Like we can talk of a shape like an oval shape, which is the first one, which stands for starting something or starting a process or an algorithm. You get me? So we also have a parallelogram, which is also to represent an input or output actions. Like example is reading a variable. A variable is a container used to hold a value. You get me? Printing an answer, what is an output action. So it does two things. It's for input and at the same time it's for an output action. We have a rectangle, which so the rectangle represents an active process. The process is that is it can be a variable assignment, it can be an evaluation. So that is so a rectangle represents a process step. And when you look at the process step, looking at it critically, you are looking at process like a step within an algorithm which carries with with does something like doing mathematical calculation, declaring a variable. These things are normally what we classify under the process step. That is, and we use the shape rectangle to represent it. Diamond represents the decision. That is in flowchart or flowcharting standard. We use the diamond sign to stand to represent a decision so that we are looking at it. If it is true, we take a 10. If it's not true, we take another 10. That is what we mean. We also talk about the arrows. Arrows are the flow or the order of operation which we can, that is either an arrow either goes forward or back. It's the forward or the backward side. So that is it. We the three core control structures. Looking at an algorithm according to Bohm Jakubin's structure of that's the structure theory. It is all about the foundational control architecture. If you look at an algorithm, we said algorithms are step by step unambiguous process or procedure for solving a problem. So it means that once we are doing something step by step, there are some control structures we have to in between the procedures. We have to go through some structures. And these are the structures that we're talking about. So we can talk about the sequence. We can talk about the sequence is just that is a build up. So when you tackle when you look at the sequence control structure, we're looking at an algorithm which involves no stepping. That is it's a gradual linear formatting which we execute a single step after another step after another step. And we can also look at the second one, which is selection. Selection talks about conditions. Conditions are the decisions that we make, and we use some control structures like if functions, if else, and all those other structures so that we can select our conditions. So iterations are also an area, and that is in an algorithm. You can have a situation whereby we have a repetition of code, and and the only way to make the code simplified and basic or compactable is probably because some codes keeps on repeating. For instance, if you're counting a number of if you're counting numbers, so even that you from one, two, three, you're doing the same thing over and over again. You are adding plus one, so it's a loop. And you have so many types of loop. You have while loop, for loop, and that is so. So we can talk about according to Bohm Jacopini's theory structure, which centers on algorithms. That is, it talks about the foundational control structures that are used in algorithms. We can talk about sequence, we can talk about selection. Selection is based on conditions. And iteration, that is how the looping. Iteration is repetition of code or multiple repetition of code or blocks of instructions. So that is according to the so we can look at so if you look at algorithms, we can also touch on the idea of pseudocode. And pseudocode, as said, pseudocode is code that has an informal set of what is informal code that we use to explain things. So the idea of pseudocode is just to give a descriptive idea of an algorithm. We are just describing how it is. So we have here some key algorithms which is all about pseudocode. So some syntax patterns in pseudocode. First one is variable assignment. So if you want to set or to assign a variable in pseudocode, these are ways you can set total to zero or count equal to zero. So you can there should be an equal sign, then you assign it to the other. So input and output. So you can the keyword is input user age. Also talk about output access granted. That is how it is. So the control, the conditional path selection, we use the if else. So if score is greater or equal to 50, then output pass. Else, so the else here we'll talk about other ones. Output fail. So we can talk about the loop. So the last section is that's the conditional indefinite iteration. So we are looking at the loop. And in this case, the loop we are using the example that I was giving is a while loop. While dynamic condition is true, do some executionable steps. Then after the condition is not true. So if the condition fails, here they say while the condition is true, the steps will be executed. And when the condition becomes false, it will stop and the while will end. So we let's look at how efficient an algorithm should be. An algorithm should be efficient. What does it mean? It means that it must an algorithm must be resourceful, it must solve problems, it must be potent. So and that this we look at it from two perspective. I'll touch on the time complexity. So if a computer is complex, it checks it looks at time complexity. It means how much time does the execution take function of an input. So if there's an input, we said earlier on that algorithm, the characteristics of an algorithm, we said it must have an input. So if you input a task, how is the executionable time? How much time does it execute? So that is the time complexity. Look at the time. So and we always for an algorithm to be efficient, we look at the time. We look at the time so that the algorithm it, an algorithm should be able to solve a problem or a task within it must be finite. It shouldn't take forever. So the time complexity is a key field, a key area of understanding because every algorithm should be able to do a certain thing and it must do it well within a short period of time. The space complexity. Whilst an algorithm is executing within a stipulated time, it it must also absorb a reasonable amount of memory and resources because if you look at a computer works on memory and we shouldn't have a case whereby a set of instructions one instructional set It's just taking over everything. We don't want to face it. We don't want such a case. What we are looking at is that if you pick an algorithm you must work within a stipulated time, all right. Also, it must work within its stipulated memory. It- So that is the space complexity. So how much workspace memory can the algorithm economically related to the so, which is a very good concept or very broad concept in computer science, and it is a mathematical notation describing the asymptotic upper bound of growth. So some of the under the big O notations, we have O of 1, O of n, O of n square, we have O of log, and other. And all these are, all these are, all these big, the big O complexity, the big O notations, in them, we look at the time complexity and space complexity. That is, each of these big O notations have a section of, or it's normally time and resources. So if let's say you want to create a program, it is good that you look at this area so that you better understand or grasp the idea of the your algorithm and how much time your program utilizes the task. That is one thing. So there's a case study that we have to carefully go through, and the problem of the case study, that is finding the highest number within an assorted list, and unsorted list of n integers. So we have this is algorithm. So you input your list, that is your list, the list in question. So the list in question is, so we are using to contain some n number of elements. So in here this an algorithm you are trying to solve. So if you're asked to find the highest number with given that you have a list of integers which are unsorted from, it is just disordered. You first of all have to um, in actual fact, if you are to write it in the pseudocode, like a lame person or a normal person will, will say that you first of all arrange the numbers from the smallest to the highest. Having the numbers, you arrange them one by one. You compare each one, arrange them. Then you, after everything, you pick the highest. So what we have on the screen is just a simplified or uh, like a pseudocode format, which is representing or which is trying to solve the problem statement. That is finding the highest number being an unsorted list of integers. So that is what we have here. So before we leave for the class, so the last the last session we'll touch on is small challenge that I have for you. So this is just some algorithmic problems that I want you to use your crack your brain and you come out with concrete. At least just try your strength and find a way to solve it. So this is just so the last section is just uh, challenge that you have to uh, look at. So it's just you are given a list and you are to execute using a dry run step. That's use your you have to try running the or solving a problem with pen and paper, and you look at it. That is, you are finding currently you are finding the find mass. That is finding the highest value in that set. And from what we see here, the list is on other. So yes, that is you have to go through the steps. You have to give us the syllable and the edge case diagnosis. So that's the build up of the first uh, exercise. That is, the action is what occurs if the algorithm takes an empty list or a list where all values are identical integers. So the action is what if the algorithm takes an empty list? So what if the list that previously that we had were to be empty? What would that mean it is? Or what if the integers were identical? So does it violate the definiteness or finiteness rules? That is also a point that we must. So I want us to look at the revisit our knowledge on this about guidance, and also um, go through these questions, and let's see how we fare. And on the next section, when we meet, we revisit this session and we talk about the outcomes and how we need to crack our brains and know how to solve it. Dr. Frederick, and thank you for having the time to stay with me throughout the lesson. I'm happy and God bless you for sticking with me throughout this session. Thank you.